Hi, my name is Erwin Quiring from TU Braunschweig, and my talk today gives a comprehensive introduction to image scaling attacks, a novel class of attacks that we need to consider in machine learning. So if we consider a typical machine learning pipeline, usually we need to pre-process data for machine learning. In computer vision, we cannot pass an image directly to a learning method, for example, neural network, as learning methods typically expect fixed size inputs that are even relatively small, for example, around 300 pixels in each dimension for the state-of-the-art model Inception v3. So we need to scale images, and normally we would expect that the downscaled image corresponds to the input image, like for the one-way sign here. Unfortunately, the scaling step can create a completely different output image, which is the result of an image scaling attack that I applied here on this example. In this talk, we will analyze such an attack in more detail. To this end, let's shortly consider how an image scaling attack works. The overall objective is that an image changes after downscaling. The adversary has two images, the original source image, a do not enter sign here, and a target image, the no parking sign here. Now, given the target image, the attacker manipulates the do not enter sign here such that its modified version before scaling is still showing the do not enter sign, but becomes the no parking sign after downscaling. This attack is solved as an optimization problem. We seek for a minimal perturbation delta that can be added to the source image such that the downscaled result is close to the target image. In summary, the adversary has two goals. The output image must be similar to the target image, and the modified source image must be similar to its original version. This attack aims at the pre-processing step, which is at the very beginning of a typical machine learning pipeline, so that the implications for machine learning are manifold. First, an adversary can trigger false predictions at test time by creating a downscaled image of another arbitrary class. In contrast to adversary examples, the input to the network is an instance of a target class already, so we do not need somehow to exploit weak spots in the network. An attacker can also use scaling attacks to hide manipulations in the training dataset. For instance, she can insert backdoors that only become visible after downscaling, like here with a green box. And by using these stickers at test time, we can completely control the network's behavior. Finally, scaling attacks are of course also relevant outside of machine learning. Whenever images are scaled, think about the image preview on websites. We need to keep in mind that the threat model of scaling attacks is different to previous attacks, like the generation of adversarial examples. The attack is independent of the model, learning method, and training data, and we just need to know the parameters of a scaling operation. Standard libraries like TensorFlow have only limited number of scaling options, so these parameters are not so hard to find out. The previous slides strongly underline the severe impact of scaling attacks and therefore the need for a comprehensive analysis of these attacks. In our work, therefore, we analyze the root cause of these attacks so we can really understand why and when the attack works. This allows us to derive defenses that prevent the attack. And of course, we consider an adaptive attacker who knows about the defense, and we show that it is still not possible to circumvent the defense. In this talk, we will look at the first 2 points, the root cause and the defenses. So let's start with the root cause. To this end, let's recap how scaling works, and for the sake of simplicity, we consider a one-dimensional signal here. The scaling operation can be described as a convolution between the source signal and a kernel function, similar to the convolutional layer in convolutional neural networks. For each position in the downscaled image, the kernel combines a set of pixels from the source image using a specific weighting. In other words, the kernel is a window that we move over the source signal, and each pixel within this window is multiplied by a respective weight. As an example, let's assume we want to scale the signal here on the slide with 9 pixels to 2 pixels. We put our kernel window on the signal so that we multiply both pixels inside this window by the respective weight. Next, we move our window to the next position. Here just 1 pixel falls into the scope of a window and we simply copy it. That's it. This example depicts bilinear scaling as implemented by TensorFlow. We can now observe 2 interesting points. First, Not all pixels equally contribute to the downscaled output. Only pixels close to the center of the kernel receive a high weighting. And second, if the step size exceeds the kernel width, pixels are even ignored. In this example here, we had to use larger step size as we scaled an image from 9 pixels to 2 pixels, and only 3 out of 9 pixels were used for downscaling. Therefore, an adversary only needs to modify those pixels with high weights by setting them to the target value, and the rest of the image remains unchanged, as the example here shows. In this way, we achieve both goals of the attack. After downscaling, we exactly obtain the target signal that we want, but before scaling, we only modify a small portion of the original signal. Many pixels can keep their value, and the adversarial signal is rather unnoticeable. The success of this attack therefore depends on 2 key parameters. The scaling ratio, which determines the step size of the window. Therefore, the larger the step size, the more pixels can remain unchanged, and the attack can be less visible. And the kernel width. The larger the kernel width, the more pixels are considered for downscaling, and the attacker needs to modify more pixels, and the attack becomes more visible. Different scaling algorithms and libraries differ in the definition of this kernel window and the moving operation. And interestingly, it is quite common to fix the kernel width irrespective of a scaling ratio. So while the adversary cannot control the kernel width, she can control the scaling ratio, enabling a scaling attack. This root cause analysis gives us a very good understanding why the attack works, so we can now derive effective defenses to prevent the attack. An important requirement for practice is that we want a secure scaling operation without the need to change the API of image scaling. Otherwise, if the imaging library rejected an input as attack, we would somehow need to deal with this rejection in our machine learning pipeline. As a first defense type, we start with a conception of an ideal robust scaling algorithm so that we can check the robustness of existing scaling implementations. For instance, a secure scaling can be achieved by adjusting the kernel width to the scaling ratio such that the windows overlap. A scaling attack is then not possible anymore. As a second type of defense, we develop a method that reconstructs the source image, and it is therefore applicable to any scaling algorithm. This slide also shows an example for this. We see some pixels, and the red points represent the pixels that a bilinear scaling algorithm will use to compute the downscaled image. And these pixels were modified by an adversary. Fortunately, as a defender, we know which pixels are used by the bilinear scaling algorithm, and the idea is to repair them. So we select a pixel that the bilinear algorithm will use, define a window around its neighborhood, compute the median of this window, and use this value to repair the pixel. Then we proceed with this method with the next pixel and define a new window around it, compute the median, and use this value to repair this pixel again. We repeat this step for all pixels that the scaling algorithm uses. In this way, the adversary needs to change the pixels in these windows as well. And we show that it is generally not possible for an adaptive attacker to bypass such a defense. For evaluating the attacks and defenses, we consider 3 common imaging libraries. We test all implemented scaling algorithms and use the ImageNet dataset to have a realistic image setting. First, let's check if a downscaled output corresponds to the target image. As we can see, the attack is usually successful for all algorithms and libraries. However, we have another goal. The modified source image should be similar to its original version. Our evaluation shows that the success of attack here depends on the scaling ratio and the algorithm or library. At this point, I'd like to refer to the paper for more details. Finally, let's briefly check our reconstruction defense. This defense prevents all attacks in our evaluation. And even better, the reconstruction increases the visual quality of the modified source images because we remove the adversarial pattern. And we can even get the original prediction before modification. To give you a short intuition what that means, Here we can see that the first image depicts a modified source image that becomes the second image after downscaling. But if we apply our reconstruction method, the restored image looks cleaner, and after downscaling it shows what we would expect. So in summary, scaling attacks are a new class of attacks that we call preprocessing attack. And they need to be considered in addition to traditional attacks like poisoning, model stealing, adversarial examples, and so on. Our work gives a first comprehensive analysis of these attacks by providing a comprehensive root cause analysis that allows us to derive effective defenses to prevent the attack. To verify the threat in practice, we evaluate these attacks and the defenses comprehensively with common imaging libraries in machine learning like TensorFlow. Last but not least, thank you very much for your attention, and you can find more information on our website or of course in our paper.